So what I'm going to do next is I'm just going to ask for your answers, but I'm not going to judge them. I just want to hear them. I'm not going to say, yeah, that's right, or it's really this, or that's really good. I might occasionally say that's really good because apparently Cole's got an awesome answer for me. But there are certain questions that I will not give you the answer for right now. But over the course of the next 40, 45 minutes, I will. Okay, so really this first 10 minutes, first 10, 15 minutes is for me to understand what you think right now, and also for you to understand what you think as a group, collectively, and then see if that changes in the next 45 minutes. Okay, Jonathan, you with me? Okay, so number one, what is a scientific model? Give me an example. Any volunteers? I'm not talking about the guy that wears the lab coat on the front of the science equipment catalog, not that kind of model. Hey, good one, eh?
One of those little things that you make so you don't mind something.
Cole says it's one of those little things you make to explain something.
Like, no,
Does it have to be little?
A 3D model. Pretty big if you want.
So it could be bigger than the object
Yeah.
that it really is.
Yeah, because
Okay.
like an atom.
But it could be small. Right, okay.
3D model is
Okay, like would there be one in the room kind of thing that,
that's literally.
you know?
That's
Oh yeah, like the globe right there, right?
from that person thing that's like all.
Yeah.
Oh, like the man.
Yeah.
Okay, that'll be a model. Is the globe a model?
Yeah. Or like that sign, that thing next to the breakfast.
Yeah, that's more of a device. But what about, is that a model?
Yeah.
Chart. The chart. Would you say that it gives structure, gives you something tangible to work with when you're explaining something?
Yeah.
Well, yes, I mean,
Yeah.
no,
I would-
because it doesn't break down all those little things and stuff.
No, but it's used, it's something physical that's used to help explain how the elements sort of work together, right? Okay. Again, I'm not saying right or wrong, although the globe is. Okay, you guys are listening, right? Because I see people now listen, and I'm looking right at Johnny because he's one of them.
Yeah, Johnny.
Number two, what is a scientific law? Give an example. Volunteers, anyone? Brett, scientific law.
A law is a proven theory with facts that happen, like Newton's law.
Okay, Newton's law, I will agree that is a law. He said a proven theory. That's kind of what Brett said, right? Yeah, same thing, proven theory? Sure, you have your hand up. Proven theory. Who would agree with that statement? Okay, quite a few of you. All right. What about a scientific theory?
It's theory. Theory is like a reasoning behind something.
Yeah.
By experiment.
The reasoning behind something. Okay, this is not what I usually hear. Go ahead, Brett.
I'm smart.
It's similar to the law, but it has not been proven. It's like a guess or no.
Okay, so that's what I usually hear. So similar to a law, but not been proven. Who agrees? Quite a lot of you. Some of you are paying attention because you're doing the laugh.
Leo,
He's got a way, doesn't he? Yeah. You're a funny guy, Leo. How do we prove scientific theories then, Brett?
experiments.
Experiments? Would you say collect data?
Experiments.
Do observations, experiments? Multiple people do that kind of thing, right? Okay, what about believing in atoms? Who believes in atoms?
You split one, it goes to boom.
Ever seen one?
Technically, yeah.
Explain, Zane. There's usually one that says that.
I know, it's like.
You split this out.
I mean,
Absolutely, it's not wrong.
There's no atoms in this chair, it's plastic.
What?
What is it? Atoms are in everything?
Plastic is everything.
Because they have batteries,
What?
Atoms are in everything.
Do you understand the meaning of the word everything, sir?
Yeah.
You proved yourself wrong.
You literally just proved yourself wrong.
Atoms are in everything.
Yeah, you said atoms
Yeah.
are in everything, but not in the chair.
No, they're not.
So how do you tell what is and what isn't? Yeah.
But they're not in everything.
They're not in anything.
So plastic comes from the environment.
You want to explain to me
I think what she's getting at, and Sarah, I'm trying to put words in your mouth here, I'm trying to help you out here, okay? I think what Sarah's trying to say is that things that are not natural, that are manufactured, is that what you're getting at? Hey, can you give me an example of something else then that you, so just plastic chairs?
No, but it's like man-made.
Okay, so like, so
Yeah,
guys,
not an atomic bomb.
But they make it
Hey,
from.
let's say,
things
let's
that are
say,
natural.
like, something like, I guess I'm not, okay, so make sure that I have time. I gotta keep moving, I gotta keep an eye on the clock here, because I got certain things I gotta get done. So, my point here is, I'll get to you, Paul. My point here is that you all believe, for the most part, in atoms, but you've never seen a single one, but Zane is 100% correct. There's tables of atoms. So he could say, yeah, I've seen an atom, I've seen lots of them. But you've never seen a single one, right? Okay, stay with me here. So, generally someone says, we believe in atoms. Generally someone says we believe in atoms because we've been taught that in school. Like you've sort of, would you agree, we've deferred to someone that knows what they're talking about. Like you believe them, right? Your grade 4 science teacher says inside tables there's atoms and they look like this. You go, okay, well he's a smart guy, I believe it. Right? As long as it hasn't been a hoax that we've sort of brought you up, all the science teachers across the globe, we have it. Right? Okay, so atoms, good. Okay, so Cole is dying to tell me how science and art are similar. Or different.
Similar. Similar. They both start on blank canvases.
Oh.
What if you not use the
That's pretty good.
Shut up, Dawson.
No, what he's saying is that they both start from nothing,
Yeah.
and you put some together. Wow.
That's how science
I'm
works.
impressed.
Philosophical.
This is me impressed. It is philosophical. How about this one for you? This is the one I usually give kids. I might use that one in the
Did you
future.
put that quote on the wall?
I might. Cole, I might just put that on the wall, because that's like the Cole Freecourt statement.
Heck yeah, you gotta like put it in quotes and everything.
I might just do that. You remind me. You remind me. Okay, so my usual statement here is, do you have to know something about science to truly appreciate good science?
No. No. No.
No?
No.
Well, I mean, what if I knew nothing about science, but I like my TV? That's science.
No, but what I'm saying
Put it
is,
together.
To appreciate
no,
the art of putting it together, you have to kind of understand how to put it together.
Yeah.
yes, that's what I'm saying, right? You have to have some basic kind of understanding. Jonathan, again, you're not listening. You have to have some basic kind of understanding about science before you can truly appreciate sort of science that's outside your scope, right? Like to understand it, you have to understand it, I guess, right? And the same thing with art, right? Like you and I can look at a painting, because I'm not an artist. I can look at a painting and go, well, I don't know if it's good or not, right? You have to kind of understand something about art to truly appreciate good art. And that could be true for any kind of art.
Yeah, it's like
Yeah, like music too, right? Absolutely. Any art, really, right? Okay, so what about different? Well, I think, Brett, you guys know what the difference is, right? Science and art are very different in that usually science has, people always give me that, well, it has a right answer, right? Well, that's only science that's been sort of accepted. I like to use the word accepted instead of proven, right? Whereas art, there is no accepted answer. Okay. Now, number 7 is kind of important too, kind of for down the road. Some astronomers say the universe is expanding, some say it's shrinking, and others say that it remains a constant size or static. How can these scientists arrive at completely different conclusions when they look at the same evidence? Go ahead, Brett has something to say.
I just think it's,
Hang on, Brett. Brett's got the floor.
I think it's because they think differently, and their backgrounds may have some different knowledge.
Okay, so they're coming from a different background.
Like,
Okay, that's kind of what I'm
what
getting
they
at.
believe in, like, might change their answer a bit.
Okay, can I take that a bit further and put words in your mouth and say, would some scientists, because they have an idea, a theory to prove, and I'm using air quotes, theory to prove that they look at data and then they look for something that proves it. as opposed to looking for something that disproves it. And in reality, that's what they should be doing. They should be looking for data that disproves it. And they would like to be proved wrong. Say that's something.
What do you believe in? Is it shrinking universe?
Oh, the universe? No, I believe it's expanding. Yeah.
That's what
I think the evidence is pretty clear there, but go ahead, Cole.
I think that they have different views and stuff because like it's changing
Yeah.
so often.
It does change, right? And new evidence is presented, that's true. But I like Brett's statement about they come to it sort of from a different viewpoint, which is kind of what I'm trying to say. Okay, last one. Can scientific theories change?
Yes.
Yeah.
Because we get new data, new evidence, right? So scientific theories can change. Okay. I'm going to show you a video. It's not very long. It's not particularly exciting, but it's rather important. Unfortunately, the gentleman kind of mumbles a bit, and he's a little long. So you're going to have to be like absolutely silent, okay? I cranked it as loud as I can. Pardon me? Oh, I have the subtitles, except they're not as good as they should be, right? But, so I'm just warning you ahead of time, you will need to be real quiet here.
opening statement.
So the law, here's a law that you just observe. Every time I drop it, or let go, I guess, every time I let go, it drops. And if you try it, it'll happen to you. And if we do it tomorrow, the same thing. It's the law. It always happens. A law is an observed regularity, an observed pattern, something that we see over and over and over. And if Brandon's at home tonight, he can say, what do you think is going to happen? And you can predict, using the law, that it will happen. Now, I heard you guys talking earlier about laws that were driving down the wrong side of the road and red light and stuff like that, okay? Yeah, not you, right? Okay. Those are what's called prescriptive laws. Laws that you should follow. You should drive down the right side of the street. You should stop at red lights. This pen should fall. And it always does.
Whoa.
Always.
It's like you should
That's called the descriptive law. It's something that will happen, right? Whereas what they're talking about is it's like a man-made law. You should do this, or you shouldn't. Okay? Now, theories actually explain the law. Okay, so the law is the pen falls. The theory is this is the theory.
Hey, this is good.
Oh, sorry, this is the law, and the theory is why it's happening.
Should we write that down?
No. You just need to sit back and get this. Okay? Now, is this a big deal? He sort of alluded to it a little bit. He talked about someone saying it's just a theory. You probably heard that before. Oh, it's just a theory. Okay? I want you to watch another video, and then we're going to talk about it too. This one's a little louder. You guys should be telling me to hit record here because AJ's at home and he's trying to listen in on this here. I want you to write down this. Speculative and robust. Speculative and robust. And this is called a spectrum. A spectrum is like a scale, like from 1 to 10 kind of thing, you know. So these are different types of theories. Speculative theories and robust theories. And speculative theories are ones that have little evidence, not well accepted, maybe not very well known, little evidence, not well accepted. Yeah, still questions. Still big questions. Right? Those are speculative theories. Robust theories have the exact opposite. lots of evidence. Well accepted by people that know what they're talking about. Like, it's one thing to be well accepted by people that don't know, right? Like, is it any good to have a robust theory that, grade 3 students all agree on? No disrespect to grade 3 students, their scientific knowledge is pretty limited, right?
You'd be
Exactly, right? You wouldn't go and ask plumbers about astrophysics. You wouldn't ask astrophysicists about plumbing. They might be a part-time plumber, who knows, right? Or vice versa. It's possible, right?
Have you ever seen people hunting?
I have. You know the guitarist from Queen, Brian May, with the big long hair? Okay? He's got a doctorate in astrophysics. He's a smart guy, right? You could have that conversation with him, right? But generally, plumbers don't speak of astrophysicists, and astrophysicists don't speak about plumbing. Both are equally important. Good to know a good plumber. Okay? So that's the difference. So now what about this climate change theory?
I think pollution and all this stuff is making climate change.
Yeah, right? So, and you learned this in grade 10, the carbon cycle, right? About how when you burn gas, you're putting more carbon into the air in the form of carbon dioxide, and it acts as a greenhouse gas and it warms the earth. Now, one of the things that Governor Perry said was, it's pretty simple stuff, really. One of the things that Governor Perry said was that the climate has always been changing. Okay? I'm going to show you a cartoon. It's only a cartoon because it's hand-drawn. You guys listen? Cool? Okay? But it's pretty good evidence. Let me just show you this, okay? Okay, so this is a timeline of Earth's average temperature. So yes, the Earth's temperature has been changing. Okay, so now this mark right down the middle here. Can you see that? It says 0? Okay, you probably can't read what it says right here. I might be able to make this a bit bigger. Yeah, there we go. Okay, so it's temperature compared to the 1961-1990 average. So they took temperatures around the globe between 1961 and 1990. Zane, you're like seriously nuts. I'm going to take that home. I need you to listen. Sorry? Did he just say I'm not going to get this anyway, so I shouldn't bother listening? Is that what he said? I'm not sure why you're here, but now you're laughing. They took the average temperature between 1961 and 1990, and that's sort of the 0 mark, the baseline. Okay, so if you go back 20,000 BCE, before the Common Era, formerly known as BC, it's now called BCE. So 22,000 years ago, the average temperature around the world was minus 4.4, minus 4.3, below that average that we're talking about, that baseline. Okay, so 22,000 years ago, Boston is buried under almost a mile of ice. The glaciers reach as far south as New York City. Okay, the world is starting to warm up. Okay, from there to there is 500 years. How many generations is that? A lot. Right? Even if you live to 100, it's still 5 generations. And people didn't live to 100 back then. They lived to 20. Okay, so by this time, humans have already spread across Africa, Eurasia, and Australia. Okay, let's keep going. You see how much it's going up? The answer is not much. Okay, now we're at 17 BCE. Right? We're starting to warm up. It's still pretty cold. Look, he's got no toque on. Okay, now they have hair apparently. 16,000 BCE. Okay, hey, it's warming up. Humans reach North America, 14,000 BCE. The edge of the ice retreats from New York City and retreats north. Okay, look at all these years as the years go by here. The woolly rhino goes, we're still -1, -2, we're still minus 2.8 degrees below average. Okay, but it's warming. But look at how fast it's warming. It warmed up by about, how much is that?
Hold on. Look at the one above it.
That's true. Let's look at that one then. So that's 1, 2, 3, so that's about 2.8, and that's about 2.2. So about 0.6 of a degree. In how long, Brandon? 500 years. Keep that in mind. 500 years, 0.6 of a degree. Ice sheets are moving away from Chicago, still warming up. Every one of these big blocks is 500 years. Well, then it gets cooler again. And then the warming resumes. Okay, now we're cooking. We're still below our average. 500 years from there to there.
Developing the farm.
Okay, 10,000. How many years have just passed from the start to here? 10,000 years. That's a lot of generations.
So cool. It only went up 4 degrees, 3 degrees.
Now you're looking at
Now you're warming. Now you're warming. Last Pokemon goes extinct.
That's what happened, 9,000 BC. It's a fact. It's on the internet. Must be true. Okay, now look what happens here. No, it's not true. It's just a gag. This is not a real fact. See, it says it right there. Okay, so now we're actually above a little bit, right? So in that 20,000 to 8,000, we've gone up about 4 degrees. That's a huge amount, right? Okay.
Pokemon will come back.
Okay, 8,000 BC, things are warmer. 7,000 BC, 6,000 BC, the wheel is invented. Okay, year after year after year, the pyramids are constructed. 3,000 BC, we're still above. Stonehenge built. Not electric guitars though. Okay, now we're back down, kind of down to the average here. We're still before the first Olympics, Greek states, Confucius, the stuff in the movie 300, but regular speed and with more clothing. Okay, Alexander the Great, you may have heard of him. Julius Caesar, the Roman Empire, Pompeii. Jesus, the historical Jesus is born. Okay, so now we're right sort of at that. How long has this taken? 20,000 years to get to there. Okay. This is all evidence that we have. It's not just made up. Okay, 1,000 years ago, Leif Erikson, Genghis Khan. Okay, Shakespeare, Newton. Now we're getting into the modern era here, right? Notice that we're just slightly below, right? 1500 BC. The next big chunk, the next big year is going to be 2000.
Watch how high.
Oh, hey.
Oh,
And that's in like, oh my god. That's in not a lot of years. That's in 100 years.
Well,
It's gone up more than
this is
Yep.
obviously skewed data.
1900, right? 2000, 2016. Look at 2000, right there.
What I'm seeing is we were good before world wars, nuclear weapons, and internet. We were all good
Wow.
before that.
And the other one here.
Oh, no, that is not.
No?
That's obviously fake.
Oh, obviously.
Skewed data for.
Now, this is the scary one here. The path we're headed on,
He's gonna kill us all.
this is if we can start to halt it, right? This is if we all stop driving cars today.
Yeah.
That's evidence, folks. So it scares me. It scares me when I hear people say, and if I sort of get a little bit emotional here, if you are a politician in 20 years and you say the words just a theory, I will be there and I will call you out and I will embarrass you. I guarantee it.
Well, good thing I'm never going to say that. Good thing I'm
Do not ever say it's just a theory. Because a theory is an explanation. And the explanation behind this is pretty straightforward. This is data. Okay, evidence. All right. Pause there. Hang with me here because I do have to get through this, you guys. I know it's been long. I understand. Okay? Get a highlighter, a pen, or a pencil. Follow along, please. Ty and Cole, you with me here? Cole, ready to go? Okay. So, science is more than just a collection of facts and observations. Models, laws, theories, and evidence all play an important role in understanding the nature of science. A scientific model is... Did you get that cue? A scientific model is a conceptual representation or idea in your head that stands for and helps explain other things, like the globe, like the periodic table. A model can be physical, a real thing, like the globe, or it could be imagined, or like a chart, like the periodic table. It could be mathematical. It could be an equation. In science, we develop models that have explanatory and predictive powers. In other words, they explain and they can predict, like the model of the universe. And we test these models in the world around us. So when Governor Perry says, well, there's still some questions around it, guess what? There's questions around every model. That's what they're supposed to do, is continually test them. That's the idea. If our model predicts our observations, we accept the model as a valid description of our world. However, if our model encounters discrepant events and fails to provide adequate explanations, we begin to modify our model or search for an entirely different one. Classic example of this. Okay? Many, many, many years ago, they believed that what was at the center of the universe? The Earth, right? And if you look at the sky at night, you will see the planets. The planets are, in fact,
Revolving around the Earth.
it appears like that. The planets are the ones that are extra bright, and they tend to wander through the stars because they don't sort of stick with the same stars. In fact, the word planets, comes from the Greek word planetos, which means wanderer. It's in one of the episodes of Big Bang Theory.
The Earth is flat.
Okay, so what they saw was, if you watch these planets go around, you would see this kind of, they call it retrograde motion, and I have to kind of wiggle it to make it fit in there. But the planets would kind of backtrack on themselves. Johnny, you're not paying attention. Okay? That's called retrograde motion. And a guy by the name of Copernicus, you likely heard of him, said, hey, something's not right here. What if, instead of putting the Earth at the center, I put the sun? And he started plotting stuff, and lo and behold, the planets didn't do this retrograde motion. They just went in a nice big circle. Right? So they changed the model. And then, of course, this is what we now believe, and it's pretty much, yeah, no? Okay. So, a good example of a scientific model is the model of the solar system. At one time, it was thought that the sun revolved around the Earth, and this geocentric model of the universe was considered to be a true representation for many centuries. The model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. A new model, the Copernican sun-centered model, provided a simple explanation of the movement of the planets, and it predicted the phases on Venus. When you look at the moon every night, does it look the same day after day after day after day? No. It starts full moon, and then it sort of cuts it down, right? And then it comes back. Those are called the phases. Half moon, quarter moon, three-quarter moon, right? Copernicus said the same thing would be true on Venus. It's just that Venus is so tiny you can't see it. So they invented telescopes, and guess what? It's true. So that was more evidence. More evidence for this idea that the sun is at the center. Okay? All right. Next paragraph here. Observations can be used to test models both externally or by thought experiments as we rethink and apply our model to new and sometimes discrepant situations. Our observations can lead us to identify regularities and patterns in nature. We call these regularities and patterns scientific laws. Things we always see. When you let go of your pen, it falls. It's a regularity or pattern. A simple scientific law would be what goes up must come down. It's the law. Even Zane can't break that law.
Oh.
We can also deduce the laws given a certain set of conditions. For example, if light is a wave, we can geometrically show that the ratio of the sines of the angles of incidence and refraction is a constant. And we often represent laws as mathematical relationships, Snell's law, Ohm's law, Charles' law, or as someone said earlier, Newton's law. Contrary to popular belief, laws are not absolute, but are often constrained to certain conditions. Ohm's law is valid only for materials, and our pressure laws are constrained by temperature. In other words, they're not always true. Laws don't always work. I gave you an example, didn't I? One that wouldn't always work? Was I talking to you guys about that? I get confused. No, wasn't you guys? Okay. Yeah.
Do hypotheses become theories?
Yeah, they do. A hypothesis is really a speculative, yes. It's sort of a suggestion, and then they test it, and then they incorporate that as part of the theory. Yeah. Good question. Okay. Scientific theories form explanatory systems for phenomena. In other words, they explain and their corresponding laws, and may include presuppositions, models, facts, and laws. In other words, the Theory can contain the law, can contain the model. It's sort of the whole package, right? For examples, Einstein's theories presuppose that the speed of light is constant in all frames of reference, and in Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. Newton's laws don't exist at the speed of light.
Sweet.
Why?
Because it's too fast.
Various reasons. Yeah.
I'm gonna
I'm trying. Okay. Here's the crucial paragraph. We must be very careful how we use the term theory. In everyday usage, the word theory often refers to an idea that is not proven, and we now know that that is, Jonathan. What did the guy say? Stay with me now.
Yes.
Rubbish. Rubbish.
Garbage. Garbage.
Rubbish. It's partially true that some theories, like many cosmological theories, are speculative ideas based on little evidence. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are also often speculative. There you go. Right? And we often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, or chemical bonding, have considerable evidential supports. In other words, there's a lot of data. Thea, do theories become laws?
No.
See, she learned.
Doesn't work.
She's lying.
Okay, thanks. It is impossible to prove our theories for every possible case, but robust theories explain a great deal, and we sometimes literally bet our lives on them. When the astronauts go into the space station, and they're strapped into a rocket, they're kind of counting on the theories being correct. Kinda. Likewise, when you hit the brakes in your car, you're kind of hoping the theory of friction kind of, holds true. Otherwise, things would be a little rough for you. See what I did there? Therefore, scientific theories lie along a spectrum from speculative hypotheses to robust explanatory systems. In science education, we often use early models or theories that are adequate for a less sophisticated understanding of a scientific concept. For example, and I hate to tell you this, Bohr's model of the atom explains all the phenomena that one might examine in an introductory chemistry program. More progressive theories require more extensive background. In other words, the Bohr model is not exactly the way it really looks. Kat, do theories become laws? See? She learned.
You gotta write that on your test. Use everything.
What she said. While it's important that our understanding of the nature of science is embedded in the context that the world is rational and can be understood, we never really know if we've achieved the most rational explanation. In science, the truth is elusive, but our beliefs must extend far beyond individual opinions. In science, we insist on an evidential argument. There is a really good TED Talk, which I'm going to show you. It says, you're entitled to your own opinion, but you're not entitled to your own facts. You can't make up your own facts. That will be tomorrow. Thank you for listening. It's been fabulous.
You told us to like crazy things.
You're welcome.
They need to hear this.